Now let's look at our next chapter, which is about, I should say next section, 20.4, work and heat. This is a picture of a container which contains gas that has certain pressure and certain volume, and this is the piston which pushes down by a certain kind of force, and there's a decrease of its height dy, and so what happened is, obviously, when we do the work to the gas, compress the gas, volume decrease but pressure increase. So this is the picture. Initially we're here, it has a large volume, low pressure, but final, because we compress the gas, volume gets smaller, volume comes here, but pressure goes up. So this is something about work done to a system which is a gas. Now we're going to discuss about mathematically how do we consider this type of problem. And you still remember this picture, and gas has been compressed by doing dy, and so this is the P of final, V of final, this is P of initial, V of initial. Now let's calculate work done. In order to do that, let's say if we do this one, work done on a gas is quasi-statically, which means very, very slow. What does that mean? That means, as a matter of fact, the pressure of the gas, it is always equal the pressure of outside, let's say. So what we do is we should say outside what? Outside, because we have to use a force, F, to push it down. The force pushes the piston down. So that force has a displacement dy. That force does work. Let's say at any moment that the force can be expressed as the pressure of the gas times cross-section area. See, the pressure of the gas is inside times the cross-section area. So actually PA is this, pressure times cross-section area. If we replace this F outside by PA, which means these two forces are cancelled. Well, theoretically, the piston shouldn't have acceleration because the force cancel. That's what we call quasi-static. It's very, very slow moving, almost static. The reason we do so is we try to get our pressure stabilized, because if we do too quick, the pressure inside containers cannot be described. A pressure versus volume diagram, any point on this diagram actually present a state. A pressure is known, it's finite pressure, its volume is known. So only the quasi-static approach will make every little move that the pressure is finite and the volume is finite, that we know exactly what is it. Okay, so that is the idea behind it. So why the work done is negative? Actually, work done is force time displacement, but now the dy is negative, because see, if this is the direction y, isn't that true? Initially we're at the higher place, now we go lower place, dy is negative. So by adding a negative sign, negative dy become positive. So the work done now by the outside force to the system is positive. Since we replace this F by pressure of the gas and cross-section area of the piston, and then combining this cross-section area of the piston and dy, isn't that true? Actually, that is amount of dV, that is amount of the volume the gas decreases. Yes, so that's how we get the work done. Total work done is the summation of PdV. See, here's P, A times dy gives dV. So this is the definition of work done to a gas system. Well, once we know that, we're going to consider what's going to happen to the gas system. Well, we say pressure change, volume change. As far as we know that PV equals to nRT, this is a ideal gas equation. If pressure change, volume change, that means temperature change. Temperature change, then it will associate with heat, because heat will be transferred when the system temperature either drops or raises. So that's why for this section we're going to consider this relationship, work and heat. Before we go on work and heat, I would like to introduce this concept, which is called First Law of Thermodynamics. If you still remember at the beginning of this chapter, I said actually the first law of thermodynamics was covered before the zeroth law of thermodynamics. Anybody still remember what is zeroth law of thermodynamics? That is something about temperature, right? If object A reaches thermal equilibrium with object B, if object A also reach thermal equilibrium with C, then B and C are in thermal equilibrium, which means they have the same temperature. So that's zeroth law. It's very interesting. Now here we go. The first law of thermodynamics. That actually is about conservation of energy. What does it say? It says the change of internal energy of an isolated system equals to the heat added to the system plus the work done to the system. Isolated system definition is the one does not interact with its surrounding. The one does not interact with surrounding, which means there's no heat exchange, there's no work done on or to. That's called isolated system. Now, isolated system, the change of internal energy, well, we talk about internal energy is actually thermal energy plus bond energy. If we do not consider the intermolecular, which is bond energy, that's basically the thermal energy. The change of internal energy is due to the heat added to it and work done to it. So for isolated system, if defined there's no heat change, which is Q equal to 0, and no work done, and then according to this, delta E will be 0. So delta E equal to 0, which means the internal energy doesn't change. Internal energy is thermal energy. Thermal energy is just a bunch of a collection of random energy molecule, which is proportional to its kinetic energy proportional temperature. So actually this comes to the conclusion, an isolated system when Q equal to 0, no heat transfer out, no work done to or towards outside, delta E internal equal to 0, which means actually temperature is constant. That's the conclusion. Actually, we will discuss more in next chapter. Next term that we need to learn is about cyclic process. A cyclic process means start and end at the same state. Well, if this is pressure versus volume diagram, let's say we start from somewhere. Do you remember we start from a initial of large volume, relatively lower pressure, that's initial, and we compress the piston, push the piston down, so the volume decrease, pressure increase, that's final. So that is initial to the final. If we want to have a cyclic process, which is this is initial, this is not final, actually it's final prime, and then we go down to here, and then we come back to here. So if we start from this point, we go through a cycle and come back to this point. This is called cyclic process. So since we go back to the original state, this is the P of initial and V of initial. According to ideal gas equation, if system is sealed, N is constant, nRT, T will be initial. So everything go back to where we start with. See? That's how we describe the system of gas: pressure, volume, temperature. So it ends at the same state, which means pressure, volume, and then certainly related to temperature. Now, for initial to final, this curve, it could be, as a matter of fact, isothermal, which means constant temperature. If we submerge this container in the temperature reservoir, which means keep the same temperature. Also, it is possible we do really quick from initial to final, we'll push the piston down really quick. It could be so-called adiabatic. That means we do it so fast, there's no heat flow out of the system, no heat flow in. Adiabatic means Q equal to 0. So for the curve part, it could be either adiabatic or isothermal. In order to do isothermal, if you want to have a temperature as constant, we have to submerge that container into a, let's say, ice-water mixture, something like that, to maintain temperature. Obviously, from here to there, when this is a constant volume, because this is the same volume, that is called isovolumetric process. And then from here to there, we are performing at the same pressure, that is called isobaric, that's pressure is constant. So we have a couple of different processes that we can choose to complete a cyclic process. We have choice of isobaric, isovolumic, isothermal, or adiabatic for the curved part. Here we go. We can take a look at this picture. And obviously, from initial to here, that is isobaric. And from here to there is isovolumic. And similar, we can go up isovolumic first, isobaric later. And from here to here, it's a curve. And it could be isothermal, that is constant temperature, or adiabatic. Why? The curved part is isothermal. Look at this. PV equals to nRT. So if temperature is constant, that is a constant. Let's make a C. So this tells us pressure and the volume is in such a relationship. It's in volume increase, pressure decrease. So that is the curve. That is for isothermal. Now, why I mentioned that it is also could possibly be adiabatic. As a matter of fact, the formula for adiabatic is pressure times volume to the gamma equals to a constant. That gamma is always more than 1. It's a number. For different gases, gamma value will be different. So let's say view the gamma is a constant but it's more than 1. So look at this. If gamma is more than 1, P versus V to the gamma is also a curve, but it's a curve which has steep slope. Because you see, this one actually is CV to the -1, but that one actually is V, the pressure. If we want to get this pressure equals to the constant V to the negative gamma, this is more than, the gamma is more than 1 right here. So volume change will cause pressure respond in a much dramatic way. So we can actually imagine if we start from initial to final, if we see something like that, the other one must be adiabatic because it has steep slope. Okay. How do we calculate work done? Okay, for different process, let's take a look. If T is constant, that is isothermal. So work done is negative PdV, since that PV equal to nRT and T is constant, then pressure can be replaced by nRT over V. So what we do is replace P by nRT over V dV, and from V initial to V final, as we can see, if the system is sealed and is constant, R is constant, temperature is constant because this is isothermal, and the result will come out pretty easy. That is negative nRT of natural log V from initial to final. So that will be negative nRT of natural log V final divided by V initial. That is the work done for when temperature is constant. Now, if we have pressure is a constant, then it is a very easy case, because work done equal to negative of PdV. Pressure is constant, you can take the pressure out, and integral dV is simply delta V. So the result is, because pressure is constant, delta V is V final minus V initial, just like that. And obviously, if volume is a constant, then there's no work done, because work done is negative of PdV. You don't have dV, then that's equal to 0. So that is the 3 common procedure of calculating work done. And we can actually, the next chapter will address how do we calculate work done for adiabatic process. That is not hard either, but we will discuss that in the next chapter.